Okay, good. So yeah, so welcome everyone. So it's my pleasure to welcome back Aamal Hussain. We'll be continuing his lectures on dynamics of games. And today he'll be talking about solution concepts arising from game dynamics. So thank you, Aamal.
Okay, thank you, Bhupendian. Yes, hello everyone, welcome. So we are going to be continuing very much where we left off from last year. I can't actually remember when the last talk was. So specifically, we were looking at game theory. We did a little bit of intro to game theory last time. And more specifically, we were looking at game theory from this different lens, the lens of dynamical systems. Right? So we're going to be continuing with that. And there's two parts to what we were doing. There's the game theory part. And then there's the lens, which we're viewing it from, dynamical systems. So I'm going to start with game theory and then move on to dynamical systems and see where the intersections are. As Bhupendian mentioned, we're specifically looking at solution concepts. So we're trying to understand, okay, both of these quite well-established theories, or fields, I should say, have ideas of what a solution is for the problem at hand. And we're going to see what each one predicts and where there's any intersections between the two. Okay, so starting off with game theory, there's going to be a bit of recap for anyone who was here last time. I will speed through it. Anyone who wasn't here last time, you can feel free to watch the previous talks, but I'll be going over it now anyway. Okay, so game theory. Gonna go over a quick example. It's the rock, paper, scissors example that we had last time. And if you recall, the idea that each agent is going to follow is they're going to want to try and maximize their payoff. Okay, and these payoff matrices are how we encode the rewards that each agent receives. So for example, if I play rock and you play paper in one of these games, then I lose and you win, which means I get -1, you get 1. Of course, if we both play the same action, then we draw and neither of us get any payoff. Okay, so that's essentially the whole thesis behind game theory. We're able to encode these interactions in some kind of mathematical structure. And what we want to do is monitor the probability with which any given action is played. Okay, so to visualize that, I'm going to use the simplex, which we talked about last time, but essentially it just is a visual depiction of where or what probabilities each action is being played with. So for example, now player 1 is playing rock with a unit probability and player 2 is playing paper, right? So we look in this cell and we see that agent 1 is losing the game, right? And what happens as agent 1 changes their action from, let's say, rock to scissors, is that the payoff is going to change because, or I should say the expected payoff is going to change because we're looking at probabilities here, because we're changing the probabilities with which we play actions. So if we monitor it specifically, if I move my strategy from rock to scissors whilst you're still playing paper, my payoff is going to increase because I'm, in an expected sense, no longer losing as often. Instead, I'm winning and you're now losing. Of course, once I start moving my strategy, you can move your own to paper, and then that, of course, affects my payoff. So essentially, all this tells us is that my utility, or my expected utility, is going to depend on my action, but on your action as well, and vice versa, of course. So what's a natural thing for these agents to do in the end? If we're thinking about rock, paper, scissors naturally, what you might imagine is that the agents might want to play each action with a uniform probability. Okay, in that case, we would see that the probability moves down to the center of the simplex. So each action is being played with probability 1/3. And that allows the payoff to level out a little bit. okay? So this solution, where each agent is playing a strategy with the uniform distribution, in this case is called the Nash equilibrium. Just for a definition, the Nash equilibrium is a joint distribution, which in this case is a product of marginals. Okay, so each agent has their own set of their own distributions, such that no agent has an incentive to deviate. Now, what I didn't write here is no agent has an incentive to deviate given the behavior of the other agent. Okay, so just to go over how that works. Let's say my agents are both playing according to this Nash equilibrium, okay, a third, a third, a third. And at this point, my expected utility is 0, right? Because if we look at each cell, each one is being played with probability 1/9. And if we sum up all the expected payoffs, we're going to get 0 in the end. Now, let's say I'm player X, and I say, okay, let's assume Y is going to stay at this uniform distribution. What happens if I just play rock with a unit probability from now on? Well, if I do that, the other agent is still playing with a third, a third, a third. So my expected utility is still going to be 0. So I haven't actually gained anything by moving away from this this uniform distribution. And so I have no incentive to deviate in the first place. Okay, and if you are agent Y, you might look and make the exact same argument and say, okay, well, I have no reason to deviate from a third, a third, a third. I'm not going to increase my expected utility. So I'm just going to stay where I am. And in essence, what that says is, if you stay fixed, I'm going to stay fixed. So as long as you don't change your action, I have no reason to change mine. And both agents are doing this. Now, from a dynamical systems perspective, you might recognize that as the concept of a fixed point, right? Essentially, if we start in this position, we're going to stay in this position. But we know that fixed points come in different flavors. You can get unstable ones. So for example, I'm sure everyone's seen this diagram before, but you knock the ball slightly in this orientation, then we're going to deviate away from the fixed point, whereas here you're just going to return to the fixed point eventually. But the Nash equilibrium doesn't tell us anything about stability. So we need a way of understanding what happens when there's slight perturbations away from this point. And for that, what we're going to do is we're going to turn to evolutionary game theory. By the way, I am kind of rushing through some of these solution concepts just because we covered them last time. But if at any point there are any questions because I've rushed through it a little bit too much, please just tell me, just interrupt me, it's absolutely fine. Okay, so stability. Evolutionary game theory allows us to capture some notion of stability. And I'm not going to go over exactly how this works here, but I would invite you guys at some point to have a look at these definitions and become comfortable with what they're saying. Because in essence, what each one is saying is, okay, let's take my Nash equilibrium. And what I'm going to say is, okay, I'm player 1. I'm at my Nash equilibrium. Okay, let's say my opponent, Y, deviates slightly from their Nash equilibrium, okay? Then I'm actually better off. I will receive a higher expected payoff by staying at my Nash equilibrium than I would if I deviated as well. Okay, that's essentially what the evolutionary stable strategy is saying. And similarly for agent Y says, okay, I'm at my Nash equilibrium. My opponent is going to deviate slightly away from theirs. I'm going to receive a higher payoff by staying where I am than by deviating along with the other agent. Okay, so what this is saying is that if we have slight perturbations away from the Nash equilibrium, both agents have the incentive to stay where they are. And that, in essence, bearing in mind, of course, these are all based on sufficiently small epsilons. What that's saying is that if we take a small enough neighborhood around the Nash equilibrium, the agents, even if the state perturbs slightly, the agents are incentivized to move back into their original position. So in essence, we've just encoded the notion of a stable equilibrium. There's a question.
Yeah, thanks. What you were saying is that you have no incentive to make the same change as the other player. But of course, if the other player moves, then I could move in a different direction, right? If they've put an emphasis more on paper, then I can move more in the scissors direction, and then I'll win. So actually, if they move slightly, I'll move.
Yes. So I just realized, thank you for this, because I realized I made the same mistake that I did with the Nash equilibrium. What I'm saying is that both agents don't have a incentive to unilaterally deviate.
Yeah, that's
so it's saying that, you know, as long as if you deviate, then I don't have the incentive to make the same deviation, and vice versa. So as you said, if one agent moves towards papers, then yeah, I have absolutely every incentive to move towards rock. But then that would mean that you would have the incentive to move towards, I would have the incentive to move towards scissors, etc. So there's no incentive to unilaterally deviate from the current strategy. Okay. Thank you for pointing that out, by the way. So, okay, so we have 2 points here. One, we have the Nash equilibrium, which is if you stay fixed, I'm going to stay fixed. And within that, encapsulated within that, is this evolutionary stable strategy, the idea that if the other agent moves slightly, or if both agents move, neither has the incentive to unilaterally deviate. It doesn't roll off the tongue as well. So I'm going to say it this way. If both agents are going to say, if you move slightly, I'm going to stay fixed. I'm not going to move with you. Okay. Of course, the stable strategy is going to be encapsulated within the notion of Nash equilibrium. It's the same way that in fixed points, you get asymptotically stable fixed points. So the asymptotically stable ones are going to be contained within the set of all the fixed points, right? So these are 2 solution concepts, and there's one more that game theory suggests that we can look into. And it's a slight generalization of the Nash equilibrium, okay? So in the Nash equilibrium, we said that we have a joint distribution, which is a product of marginals, right? So we had a distribution for player 1 and a distribution for player 2. What we're going to say for this next solution concept, called the coarse correlated equilibrium, is we're going to lift this restriction that the distribution is a product of marginals. And we're just going to say that the solution is just a joint distribution over the entire space of actions. So for example, we could have a case in which, let's say the joint distribution is that the agents play rock, rock with probability a third, paper, paper with probability a third, and scissors, scissors with probability a third. Okay. And in this case, the question is, all right, does either agent have an incentive to deviate from this joint distribution as long as the other agent stays playing according to that distribution? So again, for example, let's say both agents are playing according to this distribution. Okay, so these light colored boxes are being played with probability a third and everything else 0. Now let's say player X decides, you know what, I'm going to play rock with probability 1, whilst the other agent is still playing according to the joint distribution. Well, in that case, you still have the case that the expected utility of the first agent is 0. So we haven't actually gained anything by deviating from this joint distribution, and so neither agent has any incentive to unilaterally deviate. I'm going to remember to say that every time now. Okay, so as you might imagine, because we've just lifted this restriction of being a product of marginals, where the mixed Nash equilibrium is subsumed within the set of CCEs, okay, because it's just a generalization. So now we have the stable strategy, the Nash equilibrium, and the cause correlated equilibrium, okay? These are 3 solution concepts that game theory gives us that suggest that could occur in an interaction between agents. There are more, of course, and in the link that I sent you guys, I'll just reiterate, there's a link in the chat to a learning in games bootcamp that was held earlier this year. There's a talk on game theory and dynamical systems, which actually is quite similar to what we're looking at here. The few different results are explored there than over here. But feel free to watch that as well, because it goes into some of the other solution concepts that game theory predicts, if you guys are interested in that. Okay. So we have these solution concepts from game theory. And so a natural question to ask is, how often should we expect them to come about? And more specifically, there's different interpretations of this, of course. So from an economic perspective, it might be, if we apply a reinforcement learning algorithm or study a reinforcement learning algorithm on these particular games, what outcome should we expect? In this particular situation, what we're going to be asking is, okay, if we apply an online learning algorithm to one of these games, what kind of outcomes should we expect? Should we expect convergence to an ESS, to a Nash equilibrium, or to a CCE, a cause correlated equilibrium? Okay. And so we need a dynamic for this. Before I go into the dynamic, are there any questions on the solution concepts that we've discussed so far?
Can I just ask, in the link you sent, is it the lectures by Piliura?
Yes, it is.
Okay, thanks.
Definitely watch those lectures if you do get a chance. You'll notice in the references for these slides, Georgios's name will come up a lot because his work is essentially what leads this this field at the moment. So definitely check out that short talk if you get a chance.
And can I ask about the correlated equilibria?
Sure.
So, there's the question of how such correlation could be realized. But is it, for example, that we could see which day of the week it is, whether it's odd or even, and we do something.
We do
something. We both do something depending on that, and that ends up inducing correlations in what we do.
Yeah, that's essentially the correlated equilibrium is kind of like what you're saying, that there's some predefined agreement between the agents that says, okay, this is generally how we're going to do this. And then the agents just have to agree. Yeah. And so the CCE says, assuming that both agents have initially agreed, no one agent has the incentive to break that agreement.
Yeah.
So that is the correct interpretation.
Okay, thanks.
Okay, so the learning dynamic that we're going to be looking at is the replicator dynamic. Now, we looked at the replicator dynamic earlier last year, and we kind of went over some of the properties it has. We'll be looking at a few of those again, but definitely check the previous lectures out if you want some of the background on the replicator. So the reason why we're looking at this particular dynamic, by the way, other than the fact that it's probably, I think, arguably the most popular ODE in mathematical biology, is also because it's been shown to be a continuous time limit of a lot of no regret learning algorithms. So the sort of stuff that is applied in online learning quite often, if you take a continuous time approximation, so algorithms like multiplicative weights updates or follow the regularized leader, these sorts of things, you take the continuous time limit, you arrive at the replicator dynamic. So it's a good place to start, to say the least. So our question is going to be, okay, well, if we apply this to a game, will we converge to the CCE? Will we converge to the Nash equilibrium or to the ESS? We're going to start with the easy one. We're going to start with the CCE. Now, as I said, the replicator dynamic encodes or approximates some no regret learning algorithms. And we have this lovely result. We have this lovely result that no regret learning algorithms in general will converge to the coarse correlated equilibrium set. I'm going to commit the sin here of saying that the proof of this, it actually does follow from the definitions of what no regret learning is and what the CCE is. Essentially, the idea of no regret is that if I produce my sequence of actions, so for example, if we go all the way back, and I move from scissors to the Nash equilibrium, let's say that was my sequence of actions. And after having completed all of this, I look back and I say, okay, instead of doing this sequence of actions, would I have been better off playing any one action instead every single time? So would I have been better off playing rock in every single time step or paper in every single time step? And if the answer to that is no, then the algorithm is said to have no regret. Okay, and the connection to the CCE, I'm not going to describe here. Essentially, the CCE encodes the limit of no regret. But there's a reference down here, and again, Georgios goes into this in his talk, so I'm not going to do it here. But we can take for granted that the replicator dynamic, regardless of what game you apply it to, we're going to converge to the CCE set. Okay, so that's a good start, but we want to see if we can go a little bit deeper into this. Can we go to the Nash equilibrium, for example? And for that, we have a slightly more intricate result, which is that if a point, so for example, in our earlier example, the uniform distribution for the rock, paper, scissors game, if that's a Nash equilibrium for the game, then it's a fixed point of the replicator dynamic. And similarly, if it's an ESS, then it's an asymptotically stable fixed point under the replicator dynamic. Okay. The proof of this again, actually, you know what, I can quickly give you the intuition for this. Essentially, there's a nice property of the Nash equilibrium, which is that at this point, the reward that an agent gets for playing any action I is going to always equal the expected reward that they get for playing with their distribution X. So essentially, at any Nash equilibrium, this first term, AYI, so the reward for playing I, is going to equal the agent's expected reward, right? And as you can imagine, because of that property, this bracket goes to 0, this bracket goes to 0, and so the replicator dynamic has reached a fixed point, right? Because the right-hand side of this is all 0. But note that the converse doesn't hold, because you could have the case that the xi equals 0, right? Instead of this second bracket equaling 0. So we don't need a Nash equilibrium for the point to be a fixed point, but Nash equilibrium implies fixed point for the replicator dynamic. And the proof for the point being a stable strategy is a little bit more intricate. If you want the details for that, we have the accompanying set of notes, which are still up on Sebastian's website. So you could check those out, or the reference below. Okay. So these two results allow us to connect these properties of dynamical systems, or the properties of the ODE, to the game theoretic properties, right? So we know that the algorithm or the ODE is no regret, so we're converging to the CCE. We know that if the point is a Nash equilibrium, it's a fixed point, and we know that if it's in ESS, it's asymptotically stable. So we have connections between the game theoretic and the dynamical properties of this problem. Okay, so that gives us the natural questions that we can now actually ask. We know that we're going to converge to a CCE, so what kind of behaviors do we expect in that? And more specifically, we know that Nash equilibria correspond to fixed points of the replicator dynamic. So our original question of how often do Nash equilibria arise in practice now becomes a question of how often does replicator arrive at a fixed point, which is the Nash equilibrium, right? So this just becomes a dynamical systems problem. So let's have a look at the first one. Will replicator converge to the Nash equilibrium? And we're going to revisit the rock, paper, scissors game that we were just looking at. Will replicator reach this uniform distribution that we looked at earlier? Well, if we apply it, we can see that the answer is a pretty resounding no, because the Nash equilibrium sits nicely in the center of these toroidal structures that end up forming. And what you can see is that not only do we not reach the Nash equilibrium, but we actually stay bounded away from it from almost any initial condition. Okay, in fact, unless you start at the Nash equilibrium, in this case, your dynamics are always going to be recurrent in this rock, paper, scissors example. Okay, and there's actually, this property actually extends to all zero-sum games. So if we recall, zero-sum games are cases in which the amount that one player wins is exactly equal to the amount that the other player loses, right? The rock, paper, scissors game is an example of that. And if we take any of these zero-sum games, which has an interior Nash equilibrium like we had here, not only are we not going to reach the Nash equilibrium, but we're always going to see these sorts of recurrent behaviors which are bounded away from the Nash equilibrium. Okay, the way to prove this is actually super interesting. Again, Georges's result, of course. The idea of this proof is to apply Poincaré's recurrence theorem. So Poincaré's recurrence theorem essentially says if these two properties hold, if the volume of a set of initial conditions is preserved and the trajectories from those initial conditions are bounded, then the trajectories of the ODE, or the dynamical system, is recurrent. And what recurrent means is if you take any initial condition, look at any open set around it, then the trajectory is going to revisit that set infinitely often, right? So what did we go here? If we look at the initial condition, let's say when it restarts. Okay, if we take an open set around here, you can see that the trajectory just keeps revisiting this open set. And it's going to do that for any initial condition. Okay. So in order to prove this, we need to show two things. Number one, that the trajectories of replicator preserve volume. And also that the trajectories are bounded. Now, the nice thing about most of dynamics of games is that the analysis takes place inside the simplex, which encodes the probabilities. And the simplex is compact, which kind of takes care of the second part of it. But the first part of it is the interesting bit, the preservation of volume. This is a form of analysis which is pretty common in dynamical systems, but is not typically seen in game theory type problems. And this kind of shows the power of looking at game theory problems from this lens, okay? If we're able to apply this sort of volume analysis, we can actually take this one step further. We've shown this for zero-sum games, right? We can actually take this even further and show that any game which has an interior Nash equilibrium, right? So for example here, where we had the uniform distribution, any game that has an interior Nash equilibrium, that Nash equilibrium won't be stable under the replicator dynamics. What that essentially means is that you can take, okay, let's say you start the algorithm just slightly away from the Nash equilibrium, right? Arbitrarily far apart or arbitrarily close to the Nash equilibrium, but not exactly at that point. And then you say, okay, run the replicator dynamic. Let's see if it converges. You know, even if it's like a, I don't know, 10 to the minus 50 ball around the Nash equilibrium. And we say, okay, just move a little bit and get there. Replicator won't do it. It'll always stay bounded away from that Nash equilibrium. Which from a design perspective, it's kind of annoying because it means that when we'd like to take convergence for granted, when we want to run our online learning algorithms, for example, on our GANs or on multi-agent learning systems, it's just not going to do it. So what do we have instead? Okay, well, we don't have this Nash equilibrium property, but maybe we know that the CCE is there. So maybe that's our way out. So the question is, okay, well, the CCE doesn't necessarily correspond to a fixed point. So what kind of behaviors can we expect from the algorithm? Unfortunately, the answer to that isn't simple at all. And here we're kind of pushing into the open questions portion of the talk, because as you can see here, we ran replicator dynamic on, this is a version of the rock, paper, scissors game. In fact, it's just a slight perturbation away from the rock, paper, scissors game. And you can see that the trajectories are now chaotic under the replicator dynamics. It's moving around in a completely unpredictable way, and that's not what you need when you're trying to work on a design problem, because you'd like to be able to predict, well, I mean, especially if you're using this for training a multi-agent system, you'd at the very least like it to converge. And if you can't get it to converge, you'd like to know what the long-term behavior is going to be. And what this is saying is, even in really, really simple games, like the rock, paper, scissors game with 2 players, this isn't going to converge, and it's going to give you something really, really complicated. And in fact, this can be made arbitrarily complex. So there was this super interesting result from 2021, which was last year, that showed that you could take any dynamical system, right? So for example, here we have the Lorentz attractor, which is a chaotic system. And we could essentially find some matrix. There will always be a matrix such that if you apply replicator to that matrix or to that game, you will be able to reconstruct your dynamical system. So for example, in this case, we wanted to reconstruct, or they wanted to reconstruct the Lorentz attractor. And so they were able to find a game in which the replicator dynamic was able to produce the exact same behavior, or approximately the same behavior, right? So this is a bit of a problem, because it means that we can apply the replicator dynamic or our online learning algorithm to any given problem, and we can get something arbitrarily complex out. So at this point, what we'd like to see is, well, we don't have guaranteed fixed point behavior. We know that we can get complex behaviors coming out of this. When should we actually expect these complex behaviors? So one thing that is one sort of problem that you might want to look at is, okay, well, we've been looking at 2-player games so far. What about 3-player games? What about 4-player games? In general multi-agent settings, unless you're dealing with GAN type problems, you're probably going to have more than 2 agents in the field, right? So what should we expect this behavior to be more common in those situations, or maybe a little less prevalent? As you can imagine, the more players you throw into the system, the more likely you are to get these chaotic dynamics. And this was actually a statistical result that was shown in 2018 that essentially says that, okay, we take a replicator or a version of replicator, and we say, we increase the number of players in the system. How often do we get these unstable sorts of behaviors where we're not getting convergence to a fixed point? And as you can see, the growth is pretty, it's logarithmic, but it's quite fast. And we're at a point where we only have 100 agents, and the area of the unstable region is getting pretty high. So there becomes a problem now, because this is saying that if I have, let's say, 1,000 agents in the field, or if I have a simulation with 10,000 agents, which, for example, in swarm type problems is small, right? It's not uncommon to have, hundreds or thousands of agents interacting with one another. And what this is saying is that if you have this, just don't expect convergence of your learning algorithm, because it's not going to happen. So what we were thinking about is there a way around this? Is there something that we can do, or is there a way to approach this problem that alleviates this concern of increasing the number of players? And what we were thinking is that, okay, well, in general situations, whether it's social or in design type problems, not every agent is going to interact with everyone, right? So in typical situations, we're going to have some kind of communication network. So whether that's through social media, whether that's just through word of mouth interactions, I'm not interacting with everyone in the office that I'm currently sitting in. I know some people, they know those people, and so there are degrees of separation. So what happens if we take this into account? So what we did is we focused on the case where agents are interacting via an underlying communication network. And we said, okay, based on the structure of this network, what kind of, how does this problem translate? Will we expect more chaos or more unstable dynamics as we increase the number of players? Or is there something else that's happening? So in this particular example, we have 2 communication networks. Number 1 is in which every agent is interacting with every other agent, right? That's the case that was looked at originally. And what we're hoping is that for this network, the result will agree that as you increase the number of players, you're also increasing the number of interactions. So you should expect more unstable dynamics. But what if we keep the interactions constant? So for example, in the second network, each agent only has 2 neighbors, right? And no matter how many players you have, we're only going to have 2 neighbors per agent. What do we expect in this situation? Well, we looked at the size of these unstable regions, or how often we're getting these unstable behaviors. And as you can see, so on the left, you have the fully connected network where everyone's interacting with everyone. On the right, you have the ring network where each agent is only interacting with 2 agents, okay? So in the fully connected network, as you increase the number of players, so each bar represents a different number of players, you can see that there's a significant increase in the size of this unstable region, right? Or in the amount of unstable behaviors you're getting. However, on the ring side, it's actually not that strong of an increase, right? We're increasing the number of players in the system from 5 to 20, in fact. And there's actually not that much of a discrepancy in terms of how much instability we should expect. So actually, what we're able to see is that the number of, or the prevalence of these chaotic dynamics doesn't depend on the number of players, but on the number of interactions. And this kind of gives us a way out, where if we're designing something like a swarm system and we'd like our system to converge, what we're able to do is say, all right, fine, we can have 10,000 agents, but we're only going to keep it at 5 neighbors per agent or 5 interactions per agent. And that way we're able to curtail any problems that we might see from chaos or instability in our learning dynamics. So that's one area, that's one thing that we're able to say about the chaotic dynamics that occur in learning. We're able to say that it doesn't depend on the number of players, it depends on the number of interactions. But there's so many questions that arise from this. This is repeating what I just said, but just in a slightly more formal sense. Anyway, the questions that kind of arise from this are, okay, what else does it depend on? We've looked at the number of players, but how does it depend on the game itself? We know that we're going to get recurrent behavior for zero-sum games. We know other properties for games like potential games. But there's a huge array of interactions that we can look at in between those two extremes. Where should we expect chaos? Is there any underlying structure to that chaos? We've seen examples of recurrent behavior. When else? So for example, one of the more recent results is that, okay, zero-sum games for 2-player systems is recurrent. That result actually extends to networks of zero-sum games. So we're moving forward, but there's still a lot of questions to ask as to what the sort of day-to-day behavior is for these learning algorithms. And one of the ones that I find super interesting, and we're going to be talking, by the way, about each one of these questions as the talks progress. But one of the ones that I find quite interesting is the last one. To what extent can we actually control the outcome of these learning dynamics? Right? We know that we're operating on a compact space. We can make the assumption of a continuous learning dynamic. When can we actually control that behavior? Anyway, these are the sorts of questions that are still open, and there's probably hundreds of thousands of questions that we could ask about learning in games. But this is just a flavor. That's everything that I wanted to say. So thank you for listening. Are there any questions on everything that we've talked about so far?
Yes, there is a question.
Yeah.
About the last thing that you said, what do you mean by controlling outcome of learning?
Okay, it's a really interesting question, actually. So the replicator dynamic is a dynamical system just like any other, right? And we know that under different games, under different utility functions, the behavior of replicator is different, right? So for example, we looked at the rock, paper, scissors game and it had this recurrent behavior. But as I said, I slightly perturb the game from rock, paper, scissors and we get chaos, right? So we get very different resulting behaviors. So one of the questions that we're asking is, okay, can we apply a control on the utility function itself to control the behavior of, or to control the outcome of the learning dynamic? So for example, let's say I want a particular action to be played with a high probability. Can I apply a control on my fitness function or my utility function to ensure that that action is always played with a high probability, right? Or if I see a chaotic system, is there a way to apply a control on the utility functions again to actually break that chaos.
So this kind of control relates to predicting?
Yes, yeah, so it's a prescriptive type of problem. So it's saying, I want a particular outcome. Can I change the game, essentially, so that that outcome is realized?
So you're actually designing already.
Exactly, exactly. So that's, in game theory, it's kind of, I think it's called mechanism design, to essentially create a game to promote the outcome that you want. But again, that's something that's looked at from the game theoretic perspective. What we're doing here is applying it from, or looking at that same problem from a dynamical systems perspective.
Okay, great.
All right, any other questions? Yeah, okay. Thank you, Aamal. Thank you very much for the.
Thank you very much.
Thank you. Take care. Thanks. Take care, everyone. Bye-bye.
Bye.